Hello, friends. My name is Antonio Vasquez, and today I'll be telling you about the synthesis of lisdexamphetamine via the coupling of amino acids by carbodiamide reagents. Let's dive in. So, lisdexamphetamine, sold under the brand name Vyvanse, is a prescription medication that acts as a stimulant to the central nervous system of the human body. The structure is shown here, and as you might be able to see, it consists of the amino acid lysine. Since approved by the US Food and Drug Administration, or the FDA, in April of 2008, it's been primarily used to manage attention deficit hyperactivity disorder, or ADHD, in children, teenagers, and adults. It has been recently approved, however, for use in managing moderate to severe binge-eating disorders in adults, although it is not designed for weight loss. Getting back to the structure, though, lisdexamphetamine is a single enantiomer formula being composed solely of dextroamphetamine, shown here to possess a chiral center of S configuration. This distinguishes it from other drugs such as Adderall, which is composed of equal parts racemic amphetamine and dextroamphetamine. Now, to anybody who's heard of amphetamines or has at least watched Breaking Bad, it should come as no surprise that amphetamine is a key player in the effects that its derivatives have on humans. In fact, lisdexamphetamine itself is an inactive prodrug, but after ingesting it, enzymes in our red blood cells hydrolyze it into dextroamphetamine, which then gets further metabolized into compounds that induce effects. Beta hydroxylation generates norephedrine, which is responsible for appetite suppression. While on another pathway, para-hydroxylation gives 4-hydroxyamphetamine. This prompts the release of norepinephrine in our brain, and that results in increased vigilance, arousal, memory retrieval, and attentiveness. Now, both of these intermediates can further react to form 4-hydroxynorepinephrine, and that's responsible for the longevity of the medication. Now, looking at all this, you may be thinking, why bother synthesizing lisdexamphetamine? Why not just administer dextroamphetamine as a medication? Well, it turns out that the extra time it takes for the body to convert lisdexamphetamine into dextroamphetamine is very beneficial, as it ensures the critical metabolites we just saw are formed, and it tends to make side effects less pronounced. And that justifies synthesizing the prodrug, lisdexamphetamine. And who does that? The synthetic chemist. As with all syntheses, it's not as simple as just going into a laboratory and combining some chemicals. There are several aspects regarding reactivity and structure that we have to consider. First, we want to design the actual synthetic pathway for lisdexamphetamine. Retrosynthetic analysis shows that a disconnection at the amide linkage in lisdexamphetamine gives the retrons dextroamphetamine and, as we noted earlier, the essential amino acid L-lysine. The next thing to consider, the stereochemistry. As I mentioned earlier in this presentation, lisdexamphetamine consists exclusively of dextroamphetamine, the S configuration of amphetamine. So that configuration, in addition to that of lysine, must be S. Otherwise, we'd likely get a compound with totally different effects. Next, we have to consider that we cannot simply combine an amine with a carboxylic acid group, like we can with other carboxylic acid derivatives. And this is because that would simply result in an acid-base reaction rather than the formation of an amide. For this reason, coupling agents are often employed. The most common coupling reagents seen in peptide synthesis, and the ones we'll focus on in this presentation, are carbodiamide reagents such as dicyclohexyl carbodiamide, or DCC. However, carbodiamides are not regioselective, which means that peptide bonds can form between reacting amino acids at undesired sites. To circumvent this, protecting groups are used. In particular, we protect the amino or the carboxylic acid group of the amino acid. Now, for the synthesis of lisdexamphetamine, our retrosynthetic analysis shows that we want the carboxylic acid group of L-lysine to react. So what we want to protect are its amino groups. This can be accomplished by treatment with dicarbonates, such as di-T-butyl dicarbonate, or BOC2O. This forms a carbamate, as shown in blue. The nitrogen atom of a carbamate is less nucleophilic and therefore less reactive because its lone pair is delocalized by the neighboring carboxyl group. Removal of the carbamate group simply requires an acid, and as we'll soon see, the acid used is responsible for the salt of lisdexamphetamine obtained. Since the carbodiamide reagent is so significant in forming the peptide linkage in lisdexamphetamine, there is merit in looking at its mechanism. Again, carbodiamide reagents can generate peptide linkages between any carboxylic acid and amine, but here we will work with 2 amino acids. Now, suppose we treat them with DCC. Assuming they are protected appropriately, the first step is believed to involve the nitrogen atom from DCC deprotonating the carboxylic acid of amino acid 1. The result is a carboxylate ion of amino acid 1, and that then performs a nucleophilic attack on the central carbon atom of the now protonated DCC intermediate. Now we have an ester, and this is capable of undergoing nucleophilic acyl substitution with an amine, such as the amino group of amino acid number 2. As we'll see later, this can occur with oxygen atoms as well, which have lone pairs that are capable of being nucleophilic. Moving on, the resulting intermediate will then undergo proton transfers where appropriate. And finally, the initial carbonyl group is reformed as a result of the pushing off of the alkoxy group formed as a result of DCC. This gets us an amide bond and a diamide product corresponding to the carbodiamide used. When DCC is used, the byproduct is dicyclohexylurea, and this can be separated from the major product via filtration. And what's funny about this mechanism is that it's mostly an extension of nucleophilic acyl substitution reactions seen with other carboxylic acid derivatives. And of course, peptide bond formation with other carbodiamides have an analogous mechanism to the one seen here. All right, so now that we've looked at some aspects of synthesizing lisdexamphetamine, we can look at some real synthetic schemes used to synthesize it. All right, so now that we've looked at how we can synthesize lisdexamphetamine, we'll look at some real synthetic schemes that have been used to synthesize it. Each are taken from patents and are referenced at the end. For this first scheme, we'll start off with L-lysine, and this is commercially available as a hydrochloride salt. L-lysine undergoes carbamate formation with T-butyl carbonate in aqueous sodium hydroxide. In this case, both amino groups are to be protected, as both can unfavorably react with the carboxylic acid. After protection of the amino groups, the protected L-lysine reacts with N-hydroxysuccinimide, or NHS, in conjunction with DCC. NHS is commonly used in organic syntheses as an activating agent for carboxylic acids, and as we can see, reacting it with a coupling agent, such as DCC, our good friend, we get an activated ester. And this ester is capable of reacting with dextroamphetamine in the presence of a base catalyst, in this case, N-methylmorpholine. And that is how the peptide linkage is formed in this synthesis. Finally, hydrochloric acid is used to remove the protecting groups, and the result is lisdexamphetamine hydrochloride, one of the salts of lisdexamphetamine that is administered as medication. Now, what's nice about this synthetic scheme is that it's quite short, clocking it at just 4 steps. There are a couple of disadvantages, though. First of all, isolating the Bach-protected lisdexamphetamine intermediate involves flash column chromatography, which is cumbersome and time-consuming, to say the least. DCC is also a potent allergenic and moisture-sensitive, so it is challenging to work with on an industrial scale. Nevertheless, DCC is very inexpensive, and its amide coupling reactions often give high yields. So using it in the synthesis of lisdexamphetamine is fairly valid. Let's take a look at another reaction pathway that's been used to synthesize lisdexamphetamine. We'll again start with L-lysine. L-lysine is treated with di-T-butyl dicarbonate. This is a different protecting agent than the T-butyl carbonate used in the last synthesis, but we get the same result: protection of the amino groups. Now in this scheme, we have S1-phenylethanamine off to the side. This is going to undergo reductive amination with 2-phenylpropanone, and this forms the secondary amine shown here. This secondary amine is then treated with ammonium formate at an elevated temperature to undergo what appears to be a Leuchart reaction. The Leuchart reaction is simply an extension of the reductive amination that gives us dextroamphetamine ready to be coupled. And what happens next is exactly that. The Bach-protected L-lysine is coupled with dextroamphetamine by another carbodiamide, this time 1-ethyl-3,3-dimethylaminopropyl carbodiamide, or EDC for short. Hydroxybenzotriazole, or HOBT, is thrown in to circumvent any possible racemization of the activated amino acid. Ultimately forms an active ester and thus is functionally analogous to NHS seen in the first synthetic scheme. Coupling gives Bach-protected lisdexamphetamine, which is then treated with methyl sulfonic acid for deep protection. Note that the salt given this time is lisdexamphetamine dimesylate. As you can see, the majority of the reactions in this synthetic scheme are fundamentally the same as that of the first, but different reagents are used. Another similarity between this scheme and the last is that it too has its own set of advantages and disadvantages. It includes the preparation of dextroamphetamine, which shows how it can be prepared from simpler compounds rather than being purchased. But that makes for a longer synthetic pathway, which is more time-consuming and may cause inefficiency with yields. In terms of reagents, use of EDCI rather than DCC may be preferred because it benefits from being water soluble and less toxic. The only drawback, though, is that it's far more expensive than DCC. At the end of the day, though, the reagents used and the synthesis preferred depends on what the chemist has available in their lab, the scale they're working with, and perhaps most importantly, their budget. All right, let's recap. Lisdexamphetamine is an oral medication that, when ingested, gets broken down into metabolites to treat ADHD and binge eating disorders. Looking at the metabolic pathway of lisdexamphetamine, we got an idea of why synthesizing it is valuable and more efficient than simply administering amphetamine. Then, structural and retrosynthetic analysis showed that lisdexamphetamine contains L-lysine in its structure, and therefore it can be synthesized utilizing reactions of amino acids, whether it's protection or deprotection of their different functional groups or methods of peptide synthesis. After that, we explored carbodiamides. We took a look at the mechanism of how they form peptide bonds and even noted the good and the bad about their use. Finally, we looked at a couple of actual synthetic routes for lisdexamphetamine. Each utilized amino acid chemistry and even allowed us to point out criteria for designing syntheses, such as reactivity and cost of reagents. And here are my references. Thanks for listening.